So hello, my name is Asim Jamshed and I'm here to present MOS. This is a joint work with YoungGyoun, Donghwi, Dongsu and my advisor KyoungSoo Park. So middleboxes are increasingly popular and widespread in internet today. The trend shows that many middleboxes deal with TCP traffic as it is the most dominant transport layer protocol. Not surprisingly, most popular middleboxes operate with L4 and L7 semantics. However, building flow processing middleboxes is often non-trivial. Let me give you an example. A cellular data accounting system is a custom middlebox used by cellular ISPs that collects traffic usage per subscriber. There is no open source project, so each ISP has to build its own from scratch. The main logic is pretty simple, as it basically accounts for every packet that a user consumes. However, some ISPs do not account for TCP retransmissions, as the end user is not responsible for packet loss. Implementing this policy is tricky, as it has to check whether the content of retransmitted packet is the same as the original packet. Otherwise, one can launch TCP tunneling attack that makes all packets look like retransmissions and use the data for free. For building such a middlebox, we need a flow management module that requires tracking of complex flow level states and events for many concurrent connections, even for a very simplified stateful flow processing middlebox. So as far as the accounting system is concerned, the flow management should be responsible for reassembly buffer as well as out of order packet segments. Moreover, the flow management should be responsible for event notifications for TCP retransmissions that can be delivered to the application context. And finally, the flow manager should be responsible for storage utilities to store per flow accounting metadata and statistics. So how can one implement such flow management module for the middlebox? A developer can either borrow the code from an open source IDS, such as Snort or Suricata. However, modern IDS stack spans from everywhere from 50,000 to 100,000 lines of code. And to make matters worse, the flow management module is these days very tightly coupled with the main IDS code base, so it makes the extraction process very difficult. Alternatively, the developer can borrow the code from the kernel networking stack, such as from an open source kernel networking stack such as Linux or FreeBSD. Unfortunately, the networking stack only provides state management for one local endpoint. So what we actually need is a stack that can provide a dual stack and complete API that can provide middlebox semantics. So the developers, at the end of the day, end up developing their own flow management from scratch. Now, implementing a flow management module can get complicated, so programmers are prone to making mistakes. And for every custom middlebox application, you'll have to repeat the same process over and over again. So before I introduce MOS, let me just show you how a typical endpoint application is built. Network programmers normally use Berkeley Socket API that provide very nice abstraction that separates out TCP IP stack from the application. The network programmer doesn't necessarily need to know the internal details of the TCP IP stack that is inside the kernel to implement his own program. On the other hand, this is how a typical flow processing middlebox looks like. Developers normally build upon a packet IO stack, which can either be TPDK or NetMap or PFRing. And on top of that, the developer has to implement his own flow management logic, and on top of that, the middlebox application logic. More often than not, the flow processing logic and the middlebox application logic are very tightly entangled, and it gives rise to spaghetti code. So our goal in this paper is to build a reusable flow processing middlebox, a flow processing networking stack for modular development of middleboxes. So this is MOS Networking Stack. MOS stands for Middlebox Operating System. It provides abstraction for sub-TCP layer middlebox operations. We've exposed a number of programming abstractions. Firstly, we introduce monitoring sockets that abstracts TCP flows. Moreover, we provide flexible event notification system, and we also provide an interface for fine-grained resource usage at a per flow level. The benefit of using MOS Networking Stack for building applications is that the middlebox applications will be more clean and more modular once you use our networking stack. The developers only have to focus on the core application logic and not worry about the internals of the flow management module. Our stack is also highly scalable, and it can work on multi 10 gigabit per second networks because our stack is multi-core aware and we can easily parallelize work across cores. So, in MOS, a complex middlebox application can be decomposed into a set of registered events and event handler routines. All event definitions can even be reused across different applications. In MOS, we provide two key abstractions. Firstly, we have MOS Events that can be used to express network conditions for custom flow-based processing. Secondly, we have MOS Sockets through which we can retrieve comprehensive flow-level features, such as reassembled flow payload or our flow metadata. So this is how a typical MOS application looks like. Whenever a registered MOS event gets triggered, it invokes an event handler, which is part of the application context. And then the application can use MOS socket to retrieve flow level attributes. So essentially, the idea is that all the registered set of event handler routine will make up the entire middlebox logic. So let's now focus on the first key abstraction, which is MOS events. MOS events are any notable condition that merits middlebox processing. We have two kinds of events. Firstly, they are built-in events, which are those events that happen naturally in TCP processing. Some examples can be packet arrival event, or TCP connection initiation, or teardown, or retransmission events. We realize that not all built-in events will be enough to cover all middlebox application logic. So we let the programmers create their own events known as user-defined events, or UDEs. A UDE can be constructed by combining a base event, which is normally a built-in event, or a UDE again, along with a Boolean filter function. So let me give you an example. Let's suppose we have a built-in event for new flow payload data arrival. We can use it in conjunction with a filter function that parses for an HTTP request header. Now, this function is going to be parsing on flow reassembled payload, and if it finds an HTTP header, it will return true, and an associative HTTP request arrival UDE is triggered. Similarly, if we combine a packet arrival built-in event with a Boolean filter function that checks for an ACK flag, in ACK packet arrival UDE is triggered, which in turn can be used to combine with a filter that just keeps a check on the counter. And this way, we can actually create a nested UDE that checks for a 3-duplicate ACK arrival. Okay, so let's move on to the next important key abstraction, which is MOS monitoring socket. A MOS monitoring socket is an abstraction for non-terminating midpoint of an ongoing connection. It can simultaneously manage the flow states of both endpoints, the client side as well as the server side. So this is a marked difference from BSD socket, which can only provide semantics from one local endpoint. So for every incoming flow, a new monitoring socket is created. And the monitoring socket can be used for a vast range of functionalities, such as we can use MOS monitoring socket to monitor fine-grained TCP layer operations and metadata, such as abnormal packet retransmissions or out-of-flow packet arrival, and so on. We can use the socket to read flow reassembled data and out-of-order packet segments as well, and we can even modify or drop packets. Internally, MOS will manage all the flow management, and it maintains a dual TCP stack for it. The dual TCP stack will infer the states of both client and the server. So I'll give you an example. Let's suppose there's a TCP client communicating with the TCP server through a MOS middlebox. Whenever a SYN packet enters the MOS middlebox, first the client emulated TCP stack is updated, and if there are any events registered to it, those get triggered. Then if the server side emulated stack is also updated, and if there are events registered with it, they also get triggered before the SYN packet is forwarded to the actual TCP server. When the TCP server returns the SYN ACK, the same set of events happen, but in reverse order. And finally, when the client sends the first data packet, in addition to all the stuff that I just talked about, the receive buffer is also updated on the server side emulated stack. Now, in a typical MOS middlebox, or any typical middlebox per se, you can get anywhere from hundreds of thousands of connections at any given time. So for this, we need to have a very highly scalable event management module. So in MOS, each flow can register and change its own set of events dynamically. Some flows can add new events or delete events. Some flows can even change event handlers on the fly. So this obviously leads to a scalability problem as to how we can efficiently manage hundreds of thousands of concurrent flows. One naive implementation will be to create a copy of the event set whenever one flow changes its event set, maybe by adding or deleting an event. But this will cause a huge memory and computation overhead, especially when these many flows are flowing through a middlebox. So one common observation that we make is that multiple flows usually share the same set of events. So this can actually alleviate the problem at hand. So it all boils down to this. The challenge is that how one can efficiently find and share the same set of events wherever possible, thus reducing the memory copying overhead. So inside MOS, event management module, let me just introduce the data structures first. Each socket, which is representing a flow, points to an event invocation forest data structure that records a set of flow events. So in this example, I'm showing you a socket S1 that is pointing to event invocation forest IF1. Within the forest, we have multiple event dependency tree data structures. I'll just give you one example of event dependency tree data structure. The built-in event is often the root of the event dependency tree. And in this case, it's on-con new data, which is the event code for the arrival of flow reassembled payload. Then it has 3 children UDEs attached to it. So what happens during dynamic event registration? Suppose that there are 2 sockets both pointing to the same event invocation forest to begin with. Let's suppose if S1 decides to register for the new event E3, F3, where E is the event code and F is the associated event handler. A MOS event management module is going to create a copy of the original IF0, and it will be called IF1, and the module is going to attach E3, F3 tuple to the new tree or to the new forest. And so what happens when S2 also decides to register for the same event E3, F3? Now in the naive implementation, another copy will be created and E3 and F3 will be attached to it. But obviously this is going to lead to a redundancy problem. There are a lot of tree clones created in this manner. So an alternate efficient implementation will be to reuse IF1 for S2 if it is possible. For this, we need to have a fast searching algorithm to locate IF1. So this is where I'm going to introduce efficient search algorithm that only gets activated during dynamic event registration. Each event invocation for it has an ID which can be searchable through a hash table. The ID of the invocation forest can be computed by doing an XOR sum of hash of event and associated event handler function. During the deletion or addition of an event, the new ID of the forest can be calculated by doing an XOR of the ID of old forest along with the hash of E and F, where E is the event code and F is the associated event handler. So in this example, S1 is pointing to IF0 and S2 is pointing to IF1. When S1 decides to register to a new event, E3, F3, the new ID is calculated by doing ID of IF0 XORed with hash of E3 of F3. Whatever result we get, that is scanned through a hash table, and in this way, IF1 can easily be located. Similarly, if S2 unregisters the event E3, F3, again, the ID of IF1 is XORed with hash of E3, F3. When whatever result we get, it is scanned against a hash table, and IF0 can easily be located. And the same process is repeated again if S1 decides to unregister for E3, F3. Okay, so our interface also provides fine-grained resource management. Let me give you an example. Not all middleboxes require full features. Some middleboxes do not require flow reassembly. One example can be that of a NAT, which is only interested in looking at TCP or IP headers. Then there are some middleboxes that only need to monitor only client-side data. One example can maybe a firewall, which is just interested in looking at the client-side traffic. And there can be some cases when monitors are not interested in looking at flows after a certain threshold is met in terms of size or time. We allow an interface in which you can disable these features on the fly, either at a global or a per flow level. Our MOS stack is implemented in C programming language, and it spans 26,000 lines of code, out of which 11,000 is the MTCP code. MTCP is a highly scalable multi-core where user space TCP IP stack that was presented in NSDI 2014. Just like MTCP, MOS follows a shared nothing parallel architecture, meaning that all incoming flows are symmetrically distributed across all cores by using the symmetric RSS algorithm present in the NIC. We make sure that a given flow it gets monitored in the same core during its entire lifetime to avoid any unnecessary cache misses, cache bouncing effect. And then all the cores have mini monitor instances running on each core, and they work independently of each other. Okay, so I'll now begin with some evaluation results. In our evaluation, we try to answer two questions. Number one, does MOS API support diverse middlebox applications? And number two, does MOS promise high performance? I'll focus on the first question first. So we try to port a number of existing well-known middleboxes to MOS. We port Node 3 IDS by stripping 10,000 lines of code from the HTTP inspect and stream file management module and replace it with the MOS Flow Management and some well-defined UDEs that can actually replace the implementation behind node rule options. We also port NDPI, which is a popular L7 protocol parsing library for middleboxes, and PRADS, which is a network fingerprinting tool. So what are the lessons we learned? MOS simplifies code. Using only a few hundred lines of code, we can actually integrate the MOS management stack within the original systems. MOS also patches vulnerabilities. So in the original versions of NDPI and PRADS, signatures that span multiple TCP packets could not be detected. But since MOS, when we attach MOS, there is a built-in functionality to utilize the reassemble payload. So in this now, these vulnerabilities can easily be patched. MOS also does not degrade performance, and most versions of these applications work just as fine when compared with vanilla versions, both in terms of correctness and efficiency. We also decided to implement a number of prototype applications on MOS. We implement halfback proxy, which is a low latency proxy with proactive TCP retransmissions. We only needed 128 lines of code for that. We also managed to get hold of a cellular data accounting system that I showed in the first half of the talk. The cellular accounting system was Abacus in our case, and in the original implementation of Abacus, the code spanned 4,000 lines of code, and it included a flow management module with it. When we stripped off the flow management module and directly used MOS stack, the total number of lines of code got reduced to 561 lines. We also implemented a high-performance NAT and a firewall, and we also implemented midstat, which is a netstat version for middleboxes. Overall, the applications ported to MOS saw a 9-time code line reduction in the best case. Okay, now I'll move on to the performance evaluation. We used this setup. MOS machine was set up in inline mode, and the MOS machine had a dual socket 16-core processor, and it could see at best 60 gigabit per second of traffic. We also used 6 pairs of client and server machines, and each client or server had a 4-core processor. Okay, so for our first micro benchmark evaluation, we generated 192,000 concurrent flows in the test bed. Each client would actually download an X-byte content from the web server. For our first micro benchmark application, we ran a simple packet count monitor, which would just count packets in every flow using a packet arrival built-in event. So in the x-axis, we see variable number of cores in the MOS, and on the y-axis, we see the throughput as seen, analyzing throughput as seen by the MOS monitor. In the best case, we saw an overall average analyzing bandwidth of around 53 gigabit per second for 8 kilobyte flow size, and around 23 gigabit per second for 64 byte flow size. In our second experiment, we replaced the micro benchmark application with a simple string search monitoring application that would search for a fixed size string using flow reassembled data arrival event. And we got around 43 gigabit per second of analyzing throughput for 8 kilobyte flow size, and at around 22 gigabit per second of analyzing throughput for a 64 byte file. Overall, the performance scaled linearly in the monitor as the number of cores were increased. We also measured the latency overhead induced by MOS applications. First, we actually directly attached client and server and decided to check out the flow completion time in microseconds. For large size flows, we got an average completion time of flow completion time of 117.4 microseconds, and for small size flows, we got an average flow completion time of around 58 microseconds. When we attached the two monitoring applications, our latency overhead increased till 192 microseconds almost, and this meant an overall additional latency overhead of around 76 microseconds in the worst case. So one thing to realize is that even for a full DPI application, the latency blow-up is less than 100 microseconds. Okay, so this is the last micro benchmark evaluation result. We decided to test the robustness of the event management module, especially during the dynamic event registration phase. We again generated 192,000 concurrent flows. Each flow size was 4 kilobyte long. We set up a modified version of the string search monitoring application that we used in the previous slide, and we made the monitor register for a new event whenever a target string was detected inside the monitor. We made for the client flows put target string 50% of the time, and this is the result. On the x-axis, we have the varying number of event nodes in the event dependency tree, and on the y-axis, we see the analyzing throughput as seen by the monitor. So as you can see, as the number of event nodes in the event dependency tree increased, the performance of the event management modules degraded dramatically. This is because the event set would have to be copied every time a new event was registered. When we used our efficient version of the event management module, the performance was much better. In the best case, we got 20 times the performance improvement. So in conclusion, this paper actually dealt with the serious problem that exists with software-based middleboxes. Existing solutions suffer from severe modularity issues, code readability, and maintainability issues. We believe that if we use MOS Stack, we can get rid of these problems. We provide a programming abstraction with socket-based API. Our interface is completely event-driven, and we also have an interface for efficient resource usage with dynamic resource consumption. Our source code is now out, and you can have a look. And I thank you for your time, and I'm ready to take questions.
So as people are lining up, I have a question.
Yes.
Can you go back to one of the slides on actually the architecture? The shared nothing architecture that
yes.
you had. So basically, how does this impact the performance of applications that have a lot of shared cross-flow state, especially with a shared nothing architecture where you're not making any assumptions about cache locality of the application state?
If I understand you correctly, are you asking me like what was the effect of sharing across the cores? In this architecture, we're assuming that every thread which is running in the core is working like a mini monitor instance. So there's possibly no sharing taking place. So like you can think of like we don't want to get involved in the communication between the cores.
That's a question over there.
Yes.
Oh, yeah, Mark the ETH Zurich. Nice stuff. I have a question about timeouts. So
okay.
If I stand back and squint, this looks a lot like an event condition action rule system. Right?
I'm sorry, I couldn't hear you. Can you repeat the question?
Sorry. If I stand back and squint, this looks like an event condition action rule system, right? So these things have been around for a long time. They're very cool. They're extremely expressive, as you show, and have some great features. Traditionally, they have a problem, which is that they don't deal with time very well.
Okay.
And so it's very hard to express things like, trigger this action if no event happens before this certain amount of time, but don't trigger it otherwise, which is basically what a timeout would be.
Okay.
And so how do you deal with that?
So our API also has a timer function. So it can be treated as an event handler. So once there's a certain timeout threshold, you can launch that event, and then you can do whatever you want related to that timing sequence. So we have an API for that as well.
All right, but it's the other way around. It's kind of do this after this amount of time rather than do this if nothing else has happened after this amount of time?
There's nothing happened. I'm not sure I understood the question correctly. Can you give me an example to explain?
Sure, yeah. So suppose I want to time out a piece of state, like a connection, right?
Okay.
And so I say, okay, if no activity has been seen on this after a certain amount of time,
okay,
then delete it.
Yes. Okay.
Right?
Okay.
So I set some timer for some time in the future, and that deletes it.
Yes.
And then every other event handler that I write has to be very careful to, update some timestamp that says, here's when I last saw some activity. Otherwise, my code is incorrect. This has traditionally been the Achilles heel of ECA systems. Okay. So I was wondering if you had a solution to that, or you just make the programmer make sure that every event handler does the right state update.
So if we actually, the timer function that I was talking about can work at a per flow level as well. So if you trigger a timeout, only the flow that was attached to the timer will get affected.
That wasn't really the problem I was talking about. Let's take it offline.
Offline, yeah, of course. Okay.
Thank you. This is Alex Horn from Fujitsu Labs. My question is related to the previous question.
Okay.
And I'm interested in the semantics of the event handlers, the semantics the programmer has to deal with when using MOS. Okay. In the presence of concurrency, etc.
Okay. Can you repeat
in the presence of concurrency.
Concurrency. Okay. Can you please be more elaborate?
Sure. The event handlers that are being written by the programmer, are those single-threaded or in the presence of timers, as you just mentioned?
Okay.
Is there the possibility for shared state that can be modified by different event handlers concurrently? Okay. These type of concerns.
Right now, we don't have that interface in which we can have that kind of shared state. But that's this is a good avenue in which we can research or we can develop the API on. But right now, there's no interface for that.
But you're planning to have a look at it?
Yeah, please. I'll have a look.
Okay.
Okay.
Cheers.
All right.
Let's take one last question before lunch.
Hi, this is Roberto Bifulco from the NEC Labs Europe.
Okay.
I understand you're focusing on middleboxes which are doing monitoring.
Yes.
Is there a specific reason for that? Don't you think your model could be applied also to other kinds of middleboxes which are terminating flows, for example, and why not?
Okay, so we have a few functions in our API which can potentially terminate connections as well. So, but right now, so for example, if we have a middlebox that is a very strict firewall, like if you see any malicious signature, you just send a reset packet to both ends. We can actually do that. So we have that functionality.
My question was more also related to, for instance, if you have some middleboxes which are doing TCP optimization, so they need to deal with a little more complex processing than just terminating in the sense of closing the connection, but also providing feedback, generating packets, changing the content of the TCP.
Understood. So our current interface does not really modify the connection path to that extent, but it's an interesting problem. We can further enhance the interface, which can do that kind of modification to that much level. But right now, the basic semantic that we provide is resetting the connection.
So that just because you focused on the monitoring problem?
Yeah, only the monitoring, absolutely.
Okay. Thanks.
Okay.
All right. So that's the last speaker of the session. Let's thank him, Asim.
Okay. Thank you.